Good morning, I am Aditi studying in BSc Chemistry Honours second year. Today in this video, I am reading Inorganic Chemistry, Chemistry of Elements of second and third transition series. In the previous chapter, we have discussed the position of transition elements in the periodic table. Transition elements belong to D block of the periodic table and are located in between the S block and P block elements in the periodic table as shown in figure 2.1. The D block elements involve primarily the filling D subshells. The penultimate shell in those elements is being expanded from 8 to 18 electrons by the addition of 10 electrons. We also attempted to define the transition elements as elements which have partly filled subshells either in the elementary form or in their commonly occurring oxidation states. Strictly speaking, this definition excludes zinc, cadmium, and mercury from the D block elements. This is because these elements do not have partially filled D subshell either in the elemental form or in the common oxidation states. The elements of group 12 do not show distinctly the properties of transition elements except for the ability to form coordination complexes with ligands. However, for sake of continuity and rational classification, the elements of group 12 are included in the D block elements. In this chapter, we intended to explore the chemistry of heavier metals of D block, second and the third transition series. The heavier metals of the D block are highlighted in figure 2.1. It is interesting to note that the 3D transition series, the atomic number of the elements of the second transition series sequentially from 39 to 48. However, there is discontinuity in the atomic number from lanthanum 57 and hafnium 72 in the third transition series. In brief, the second and third transition series that involve the filling of 4d and 5d orbitals respectively include the elements with atomic numbers. Second transition series, yttrium to cadmium, 4d orbitals are gradually filled. Third transition series, lanthanum hafnium to mercury. Electronic configuration of elements of second and third transition series. The general electronic configuration of the elements of the second and third transition series can be written as where n-1 stands for the penultimate shell which occupies 1 to 10 electrons in the D subshell, while n stands for the outermost shell that occupies 1 to 2 electrons in the S orbital. It is important to mention that the elements of group 7, 8 and 9 are collectively called the platinum group metals. General characteristics of second and third transition series. We have noticed clear periodic trends down each group in the chemistry of S and P block elements. However, transition elements of second and third transition series very strong similarities in their chemistry within a group but show large differences from the elements of first transition series. This similarly is due to the filling of 4f orbitals in the elements that lie between these two rows of elements. Electrons in these orbitals shield very poorly the electrons in the outer 6s and 5d orbitals. As a result of poor shielding, the effective nuclear charge decreases with the result that the atomic covalent and ionic radii of the period 6 transition elements are reduced to almost the same as those in the period. Let us discuss the important differences and their causes. Irregular or anomalous electronic configuration. In the first transition series, the 4s electrons are filled before the 3d electrons in their neutral gaseous atoms. From scandium onward, the 3d level continues to fill regularly with increases zinc, but at chromium there appears to be an anomaly. In case of chromium, the electrons are so filled that the 4s and 3d orbitals are each half filled. This is due to the extra stability associated with half-filled orbitals. Similarly, at copper, the electronic configuration is anomalous because of extra stability associated with completely filled d orbitals. However, elements of the second and third transition series display much more irregular electronic configuration in addition to half or completely filled d orbitals. These are shown in bold letters in table 2.2. The anomalous electronic configuration of these elements are attributed to the several electron repulsions. Second, atomic and ionic radii. The atomic and ionic radii of elements of first transition series, 3D are well known. However, the atomic and ionic radii of second and third transition series elements are not known with certainty, with the exception of few elements. As we move down a particular family of the transition metals in the periodic group, there is an increase in size from first to the second transition series, but the size increase from the second to the third transition series is negligible as shown in table 2.3. Oxidation states. The oxidation states of the transition metals are higher for the first half of each row than for the latter members. Lower oxidation states are found to be more stable in case of first transition series compared to the elements of second and third transition series. The element of second and third transition series have higher common oxidation numbers than the first transition series as shown in table 2.4. Like the main group elements, the highest oxidation number of transition metal is found in case of oxides. Thus, the highest oxidation state plus 8 occurs in case of osmium in OSO4. The other compounds that exist in high oxidation states which have no counterparts in the first row are WCl6, ReF7 and PtF6. It is also interesting to know that superficial similarities in the chemistry of second and third transition series elements exist compared with the elements of first transition series. For example, Cr, Mo and W all are the foam oxides with oxidation number +6. Chromium oxide is highly oxidizing agent. Reactivity. The element of first transitions are more reactive than the corresponding elements of the second and third transition series. The lanthanide contraction is majorly responsible for the low reactivity of second and third transition series. As an example, gold and platinum are less reactive. The low reactivity is due to the closeness of the valence electrons to the nucleus because of poor screening of 4f electrons. Because of poor screening of 4f electrons, the valence electrons are very tightly bound to the nucleus and are not readily available for chemical reactions. Stability of the complexes. Transition metals have the ability to form complexes in contrast to S and P block elements. This is due to the small size, highly charged ion and availability of vacant d orbitals of low energy in case of transition metals. The element of first transition series from stable complexes with hard donors NO and F, whereas the elements of second and third transition series from stable complexes with P, S and heavier closen donors. Coordination number. The coordination number is commonly 6, found in transition elements giving an octahedral structure. The coordination number 4 is less common compared to coordination number 6 and gives either square, planar or tetrahedral structures. Complexes with coordination number higher than 6 are less common for the first transition series but are common among early members of the second and third transition series. Ligand-ligand repulsive interactions become more important with higher coordination number and thus it is the smaller ligands which allows highest coordination number. There are only few compounds in which the coordination number is 7. There are 3 geometric forms known in this case and are shown as monocapped, octahedron, pentagonal, bipyramid and tetragonally capped trigonal prism as shown in figure 2.2. The capped octahedron is shown by tungsten complex. Capped octahedron is formed by the addition of a 7th atom at the center of any face of the octahedron. The pentagonal bipyramid geometry is adopted by the anionic species. The tetragonal capped trigonal prism is adopted by this arrangement is by putting a 7th atom above the center of one of the rectangular faces of a trigonal prism. Coordination number greater than 7 are also known among the second and third row transition elements. Coordination number 8 is found in the square antiprism as in Na3. Coordination number 9 is the limit for covalently found d block metal complexes. Because this represents the full use of the 9 valence orbitals 1s, 3p and 5d orbitals, the anion has a trigonal prismatic structure with coordination number 9. Look at in figure 2.3b. Aqueous chemistry. Elements of the first transition series have a very rich aqueous chemistry. As an example, cobalt forms a variety of tetrahedral and octahedral complexes and display interesting aqueous chemistry. Other hand, corresponding members of the second and third transition series, such complexes and consequently do not have the aqueous chemistry. However, the most of the heavier metals, instead of forming simple cationic complexes, refer to form anionic complexes in the form of and halo complexes. The anionic complexes of heavier transition elements have rich aqueous chemistry. Magnetic properties. Compounds with no unpaired electrons are diamagnetic, while those with one or more unpaired electrons are paramagnetic. Most of the transition metals compounds are paramagnetic. The diamagnetic behavior is from the circulation of electron pairs induced by the presence of the applied magnetic field. This circulation produces an induced magnetic moment which opposes the applied field and the lead to the atoms. Metal-metal bonding. Metal-metal bonding is very rare in first transition series except in metal carbonyls such as Mn2, Fe2CO9, Fe3CO12 and CO4CO12, and in carboxylate complexes such as chromium acetate, Cr2CH3COO, 4H2O2, and in solid nickel dimethyl digloxime. On the other hand, metal-metal bonding is very common amongst the heavier transition elements of second and third transition series. For example, they form carbonyls with bonds similarly to those of first transition series. The heavier metals such as MO, Ru and RH binuclear carboxylate complexes. The halide ions of this type poses bond. A unique feature of a set of 5 elements of the second and third transition series is that these form clusters in which there is extensive metal-metal bonding. The complex cation have unusual structures. Both the cationic species contain 6 metal atoms arranged in a cluster at the corners of an octahedron with 12 bridging halogen atoms across the corners. In these clusters, there is an extensive bonding as shown in figure 2.4. Unlike the lower halides of 3D series, the lower halides of molybdenum and tungsten exist as hexamers. These present interesting structures. 6 metal atoms are arranged in a cluster at the corner of an octahedron with 8 halogen atoms located above each of the 8 faces of the octahedron and bonded to 3 metal atoms as shown in figure 2.5. Look at this. Chemistry of ReCl3 is interesting as it exists as a trimer. It consists of a triangle with 3 Re atoms with 3 bridging halogen atoms across the 3 corners and 6 halogen atoms that bridge to other Re3Cl9 unit as shown in figure 2.6. Abundance. All the 10 first row transition elements are widely distributed throughout the Earth's crust and the oceans. Iron is the fourth. After oxygen, silicones and aluminium, titanium is the ninth, while manganese is the 12th most abundant element by weight in Earth's crust. The remaining transition elements of second and third transition series are very scarce and taken together. These 20 transition elements constitute only 0.025% of Earth's crust in comparison with 6.2% of all the 10 first row transition elements. Molybdenum is a unique element amongst the second and third transition series that plays an important role in human body. Technetium does not occur in nature. Ionization energies. The first ionization energy of an atom is the minimum energy required to convert one mole of the gaseous atom in its ground electronic state lowest energy into 1 mole of the gaseous unipositive ion. In addition, towards the end of the transition series, the d orbitals become more core-like. As a result, these are less effective in stabilizing higher oxidation states through covalent contribution of bonding. Taken together, these factors make higher oxidation state less accessible to the right of the d block. In addition, there is a great loss of exchange energy in creating PD4 positive from PD2 positive, then ZR4 positive from ZR2 positive. Comparative study of the elements of second and third transition series. We have already discussed the general characteristics of the elements of second and third transition series with special reference to the elements of first transition series in the preceding section. In this section, we will like to highlight the chemistry of elements and different groups of second and third transition series. An attempt will also be made to compare the chemistry of these elements with the elements of first transition series. Zirconium and hafnium consist of element titanium, zirconium and hafnium. Some of the unique properties of these elements are summarized below. We have already remarked that the atomic and ionic radii of transition elements in a particular series decreases with the increase in atomic number. However, compared to S and P block elements, the decrease in the radii along a particular series is not regular and uniform. In case of group 4 elements, both zirconium and hafnium have larger atomic and ionic radii than titanium. However, an inspection of the table reveals that both the atomic and ionic radii of zirconium and hafnium are identical. As a result, these elements have similar chemistry. This is primarily attributed to the effect common as lanthanide contraction. All these elements possess outside a noble gas core D2S2 configuration. The significant difference of zirconium and hafnium from titanium is that unlike titanium, zirconium and hafnium only forms a few compounds in oxidation state below 4. Most of the stable compounds are in the oxidation state +4. Both zirconium and hafnium form the binary tetrahalides. The tetrahalides can be prepared by the standard methods. Look at this. All the tetrahalides in the gaseous state are monomeric and tetrahedral, but in the solid state, these are in the octahedral coordination through halogen bridging. The tetrahalides are readily hydrolyzed. The extent of hydrolysis, however, decreases from Ti to Zr TiX4. Compounds are hydrolyzed to TiO2. ZrCl4 is hydrolyzed vigorously by water at room temperature to give oxychloride, which is stable to further hydrolysis. The complex ZrOCl2 into 8H2, which crystallizes from dilute HCl, has been shown by X-ray to contain the ion as shown below in figure 2.8. Niobium and tantalum. Group 5 consists of the elements vanadium, niobium and tantalum. Some of the unique properties of these elements are summarized below. Niobium and tantalum occur generally together and are separated by fractional crystallization of their fluorocomplexes. The ionic and atomic and ionic radii of niobium and tantalum are almost similar but greater than that of 3D analog. Vanadium, although both niobium and tantalum are metallic, their chemistries in the V oxidation state are more similar to those of typical nonmetals. As a result, they do not form cationic complexes characteristic of a metal. Instead, these form a variety of anionic complexes typical of a nonmetal. The coordination numbers of niobium and tantalum in these anionic complexes are generally 7 and 8. The stable binary oxides of niobium and tantalum are the pentoxides, which are dense with white powders. They are obtained by the iogenation of other niobium and tantalum compounds in air. These are very stable oxides and extremely difficult to reduce. Halides and oxohalides. Niobium and tantalum form all the halides in their high oxidation states. The pentafluorides are obtained by the reaction. A unique feature of niobium is that it forms the stable pentatiodide. The pentafluorides are volatile white solid melting below 100 degrees Celsius and boiling near 230 degrees Celsius. They have a tetrameric structure that is characteristic for other pentafluorides with MF6 units and one bridging fluoride between each pair of metal atoms as shown in figure 2.11. The pentachlorides are yellow crystalline solids that are obtained by direct reaction of the metal with chlorine. X-ray study revealed that NbCl5 is a dimer in the solid state with two bridging chlorides giving an octahedral configuration around each niobium. Figure 2.12. Molybdenum and tungsten. Group 6 consists of elements chromium, molybdenum and tungsten. Some of the silent features of these elements are summarized below. Molybdenum and tungsten have the atomic and ionic radii nearly similar, but possesses greater values for the corresponding first elements here in the group 6 on account of similar radii values. Molybdenum and tungsten possesses nearly similar chemical properties. Group 6 elements display valencies ranging from group valence plus 6 down to 0. The valence plus 6 is the highest for all the elements. Molybdenum and tungsten in the plus 6 state are the most stable and the most common state. It is important to note that in case of chromium, the plus 3 state is the most common and stable state. It follows the higher valent chromium, especially in the plus 6 state, will be strong oxidant. In fact, chromium is the plus 6 state in the strongest oxidizing agent. On the other hand, are strongly reducing. The trioxides of molybdenum and tungsten are obtained by heating the metal or other compounds in air is a white, whereas WO3 is a yellow solid. Unlike CrO3, the trioxides of molybdenum and tungsten are insoluble in water, are not attacked by acids other than hafnium. In alkaline medium, these dissolve to form molybdate and tungstates that are tetrahedral in shape. Condensation of oxoanions give polyoxoanions or polyoxometallate in the presence of acid as shown. The structure of polymolybdate and polytungstate are based on octahedral by sharing of oxygen atoms. Anions containing only one kind of metal atoms are called isopolyanions, whereas anions containing more than one metal atom are called heteropolyanions. An interesting example of heteropolyanion is found during molybdate test for phosphate when yellow precipitates are formed of the composition. Thus, the heteropolyanion is halides. Interaction of molybdenum and tungsten with elemental fluorine gives colored covalent hexafluorides. Chlorination of molybdenum gives only the dark reddish dimeric pentachloride solid. It has a structure similar to that of Nb2Cl10 as discussed earlier. Technetium and rhenium. Group 7 consists of elements manganese, technetium and rhenium in the periodic table. The salient features of these elements are summarized below. Technetium and rhenium have atomic radii more than manganese in group 7 of the periodic table. Although technetium and rhenium form some compounds that are analogues to those of manganese, there is a very little chemical similarity. Otherwise, some of the features that makes the chemistry of technetium and rhenium different from that of manganese are listed below. Unlike manganese, which is most stable in plus 2 oxidation state, there are very few stable complexes known in case of technetium and rhenium in plus 2 oxidation state. There is a very little cationic chemistry in case of technetium and rhenium, not only in any oxidation state, even in complex compounds. Both technetium and rhenium have a very rich chemistry in the oxidation state 4 and 5, especially as oxo compounds in the V oxidation states. Unlike permanganate ion, which is strongly oxidizing ion, the corresponding oxotechnetium and rhenium ions in oxidation state are not oxidizing at all. Unlike manganese, both technetium and rhenium display extensive metal-metal bonding in second and third oxidation state. All the known isotopes of technetium are radioactive, can be easily prepared these days as one of the fission products of uranium. This has a half-life of 2,12,000 years and is a weak beta emitter. It is thus mildly radioactive and can be easily handled. The non-binary halides of technetium On the other hand, rhenium forms a large number of binary halides. For example, rhenium combines with fluorine to form ReF6 and ReF7 with octahedral and pentagonal bipyramidal geometry respectively. ReF6 gets readily hydrolyzed to ReOF4 and eventually to a mixture of ReO2, HReO4 and HF. It can be easily reduced to ReF5 and ReF4. Chlorination of rhenium yields a variety of compounds. The later compound is more important and can be prepared by the reaction of chlorine with the metal at 400 degrees Celsius or by the action of CCl4 or N Re2O7 at 400 Celsius. Re2Cl10 is dimer like MO2Cl10 or Ta2Cl10. The thermal decomposition of ReCl5 leads to the formation of rhenium third chloride, which exists as a trimer Re3Cl6 with the structure. In brief, because of the larger atomic sizes of technetium and rhenium in comparison to manganese, the various stereochemistries adopted by the heavier members are summarized below for quick glance. Group 8 versus Group 8, 9 and 10. A set of 9 elements constitute Group 8 in the old Mendeleev periodic table. This set of elements is also titled as the iron group and is comprised of iron, cobalt and nickel groups as. However, this set of these 9 elements are called Group 8, 9, 10 and respectively in the same way as of honor transition metal triads. It is important to point out that horizontal similarities are much greater than anywhere else in the periodic table except among the lanthanides. However, the second and third rows of transition elements behave similarly because of lanthanide contraction. The 6 heavier elements of the group, ruthenium, osmium, rhodium, platinum, being the most common with natural abundance of 10% compared with the other 5 heavy metals of the order of 10 to 7%. All the 6 elements occur either as metals or often as alloys such as osmiridium, an alloy of osmium and iridium. These elements are usually associated not only with one another but also with nickel, copper, silver and gold. The chemistries of platinum metals have some unique common features. In addition, there are several variations in their properties depending upon the different stabilities of oxidation states and the stereochemistries associated with the compounds formed. There is a very little similarity of platinum metals with that of Fe, Co and Ne except in carbonyl compounds. Carbonyl compounds are compounds of metals with pi acid ligand like carbon monoxide. In order to appreciate more the important oxidation states of platinum are listed below in the table 2.6 with the important oxidation states being shown in bolts. Table 2.6 Oxidation states of platinum metals. Group 8 Ruthenium and osmium. Iron, ruthenium and osmium constitute the elements of group 8 of the modern periodic table. Some of the salient features of these elements are described below. The effect of lanthanide contraction is less significant in the elements of group 8 of the periodic table. As a result, the similarities between the elements of second and third transition series are not so close or found in case of the earlier transition groups. The close horizontal similarities in the ferrous metals and in the platinum metals are largely due to the similarities of their atoms and ions in size. Osmium, being little larger than ruthenium, is expected to have a much higher density because of its compactness. As a result, Os is the second most dense element. One of the most characteristic features of the chemistry of ruthenium and osmium is their oxidation by aqueous oxidizing agent to give the volatile tetrahedral tetraoxides, orange colored, is formed when acid solutions containing ruthenium are oxidized, is formed by treating the metal either by burning in oxygen, by reacting with concentrated HNO3 of the two tetraoxides. Ruthenium is more stable. They have tetrahedral structures. Used in organic chemistry to add the double bonds and give cis-glycols. Ruthenium dissolves in NaOH solution and liberates oxygen. During the reaction, ruthenium is first reduced to pyrruthenate and then to ruthenate ion as rhodium and iridium. Cobalt, rhodium, iridium constituent the elements of group 9 of the modern periodic table. Some of the salient features of these elements are summarized below. Unlike cobalt, the heavier elements with rhodium and iridium occur only in RHF6 and IRF6, which are obtained by the direct reaction of the metal with fluorine. IRF6 is more stable than RHF6. Cobalt compounds similarly do not exist under normal conditions, exist as pentafluorides, whereas tetrameric with the formula. These compounds are very reactive and get easily hydrolyzed. Some small ionic sizes of the heavier elements lead to a variety of complexes. The unknown complexes of rhodium and iridium oxidation states are: both rhodium and iridium form tetrafluorides. Rhodium fluoride can be prepared from RHCl3 and BrF3. Iridium is one of the most stable states but is unstable and form only few compounds. Other compounds in the plus for oxidation state are characterized by RHO2, IrCl4 and complex anions. The chloride complex is conveniently prepared by the action of RH with NaCl in the presence of chlorine. The best known compound of rhodium is the red color complex. On boiling with water it gives, and with NaOH it gives. Rhodium and iridium give an interesting class of square planar complexes which are used as homogeneous catalysts. The stoichiometry of the well-known rhodium compound is RHCl PPH3 and it is known as Wilkinson catalyst. It is prepared by the reaction of RHCl3 with triphenyl phosphine. The well-known iridium compound is trans IrCl and is named as Vaska's reagent and undergoes oxidative addition reactions as given below. In conclusion, the various oxidation states adopted by the heavier elements together with their geometries are compiled up in the table below for ready reference. Palladium and platinum. Nickel, palladium and platinum constituent group 10 of the modern periodic table. Some of the salient features of these elements are summarized below. Nickel is second most abundant element by weight in Earth's crust. Palladium and platinum are rare elements but are appreciably more abundant than the other platinum group metals. Palladium and platinum do not form the simple carbonyl compounds like nickel, which forms nickel tetracarbonyl. The important oxidation states of palladium and platinum are second and fourth. Palladium and platinum exist as oxides, halides, nitrates and sulfates. All the dihalides are own except for PTF2. It is important to note that unlike the other halides, PDF2 is ionic. PDCl2 and PTCl2 are made from the elements and both exist in the alpha and beta form depending upon the conditions used. PDCl2 is a dark red solid and has a polymeric chain structure in which the palladium atoms are in a square planar rearrangement. Group 11, the copper group or coinage metals. Silver and gold. Copper, silver and gold, also referred to as a coinage or currency metals, are placed in group 11 of the periodic table. Some of the salient features of these groups are listed in the table below. There are noble metals and often occur native in nature. All the elements of group 11 are known for their highest electrical and thermal conductivities in the periodic table. Although these elements in their atomic states have a filled d subshell, these are considered as transition elements because their plus 2 and plus 3 state possesses incompletely filled d subshell. Typically, these elements exhibit variable valencies. Although copper, silver and gold display similar electronic structures and possesses high ionization potentials, yet there are only limited similarities between their properties. The most common oxidation state of silver is plus 1. It forms a variety of salts with various anions in plus oxidation state. With the expansion of nitrate, perchlorate and chloride, most of the other salts of silver are insoluble in water. The commonly heard silver chloride is insoluble in water. Structures of silver salts are usually similar to those of alkali metals. For example, the silver halides have the sodium chloride structures. It dissolves in ammonia to give a soluble complex ion. The most usual coordination number of silver is 2 linear with sp hybridization. The linear coordination is achieved with angle as 180 degree. Where L is a monodennate ligand, linear structure cannot be achieved by a biident clating ligand. For example, AgCl reacts with ethylene diamine and give a dimeric space with En acting as a bridging ligand instead of clating one. Similarly, some other soluble complexes of Ag plus are. Silver cyanide has a linear polymeric structure as shown, whereas the silver thiocyanide possesses the non-linear structure as shown below. Cadmium and mercury, heavier elements. Zinc, cadmium and mercury constituent the elements of group 12 of the modern periodic table. The slide features of the elements of group 12 are listed in the table below. Look at the table. These elements all have D10 S2 electronic configuration and typically from M2 positive ions. All the elements and their ions of group 12 have the complete D shell. These group of elements do not qualify themselves to be typical transition elements. However, because of the complexes ability of these elements with ligands, these are included in the transition elements. Zinc and cadmium display similar chemistry, whereas behavior of mercury is appreciably different from that of zinc and cadmium. Mercury is unique in many respects. Example, it is a liquid at room temperature and is a noble metal. Both zinc and cadmium react with non-oxidizing acids to liberate hydrogen. In addition, mercury is the only element in this group that forms compounds in plus oxidation state. The increased stability of the lowest oxidation state in the heavier elements in the group is more typical of the p block elements than the transition metals, whereas the highest oxidation state is more stable as discussed earlier. All the elements of this group form the dihalides with fluorine, chlorine, bromine and iodine. Thus, all the 12 dihalides of the formula MX2, where X is equal to F, Cl, Br and I, are well established. The fluorides have appreciable higher melting points than the other halides and are appreciably ionic. The melting points of the chlorides, bromides and iodides are fairly low and suggest these halides to be more covalent. Mercury form an interesting class of HGI compounds in which two mercury atoms are bonded. are bonded together. Mercury is unique in forming stable dinuclear metal ion Hg2 2 positive. All the mercury halides are known. Hg2F2 is hydrolyzed by water and then disproportionates. Look at this. HgCl2, Hg2Br2 and Hg2I2 are insoluble in water. The nitrate Hg2NO3 2 into 2H2O is soluble in water and contains the linear H2O, Hg, OH2 2 positive ion. All these elements form oxides MO and sulfides MS. By heating the elements together on stronger heating, HgO decomposes, and this has been used for preparation of oxygen. Look at this reaction. All the three elements form insoluble sulfides. CDS is a yellow and HGS is a black, whereas ZNS is white.